Hey everyone, welcome back to Control System Lectures. We're continuing our journey through discrete control, and in this video we're going to expand our understanding of the bilinear transform. And in doing so, we'll learn about how this transform warps the Z-plane, what that means for us, and what we can do about it. Now this is going to be a meandering journey, but I think the topics we'll cover will be necessary in order to set up the proper context around Z-plane warping. And this is like a 25-minute video, which is a long time, I know. But to entice you to watch the whole thing, at the end there's going to be this pretty sweet animation. So hopefully you stick around and find out what it is. If you've missed any of the previous videos on discrete control, you can find their links in the description below. Let's get to it. There may come a time in your career where you are asked to design a filter that will be implemented on a digital computer. How do I go about doing this? You might ask a helpful friend. And they say, it's easy, just design a continuous filter with the properties that you want, convert it to a discrete filter with the bilinear transform, and then ta-da, you can implement it on a digital computer. Which you promptly try and find that the performance is not what you were expecting. The frequency is all wrong. Why is that? Well, to answer this question, we first need to talk briefly about filters. You can think of a filter like a sieve or a strainer that you'd use in cooking. Its main purpose is to take a set of items and remove specific unwanted items from that set. For example, after you finish boiling pasta, you have a pot of pasta and water. You then pass the combined pasta and water through a strainer or a filter, which will allow the water to pass through and be discarded so that you're left with only the pasta. Similarly, filters can also be used on signals, like the voltage coming from a sensor. Over time, the voltage from the sensor is changing, and you can see the frequencies that make up that time domain signal by viewing it in the frequency domain. Now, you may not want to keep the raw, unfiltered signal because it could be a mix of frequencies that you want, the pasta, and frequencies that you don't, the water. So we can design a filter that removes or stops the high frequency signals from getting through so that our system only sees the low frequency sensor information. Basically, our system is only getting the pasta. In an ideal sense, a signal filter could be specified by stating exactly which frequencies you want to keep or pass through the filter and which frequencies you want to stop or reject with the filter. These ideal filters have names like low pass and high pass and band reject, or sometimes called the notch filter, and band pass. Low-pass filters keep frequencies below the critical frequency and reject or attenuate frequencies higher than it. High-pass filters are the opposite. They keep the frequencies above the critical frequency and reject those below it. The difference between these two filters in our cooking example is whether you kept or threw out the water. For pasta, you'd keep the large, low-frequency noodles and discard the higher-frequency water. But for tea, you would keep the water and a few of the smaller high-frequency tea particles. A notch filter is a low-pass and a high-pass filter that don't overlap, such that there is a band of frequencies in between the two that are rejected, and everything above and below that band are kept. You might set up a notch filter if you're trying to remove the humming noise in an audio system at 50 Hz or 60 Hz, the one that's generated by the power line. A band pass is the opposite of a notch filter, such that you only pass through a narrow band of frequencies and everything above and below is rejected. For example, our eye is a bandpass filter for visible frequencies in the EM spectrum. We can only see those specific frequencies. And further still, colored objects are bandpass filters for that specific color frequency. If you shine broad spectrum light onto a red apple, only the red frequency is reflected in the band that our eyes can see. And sometimes we only want the metaphorical red frequencies to get through our control system, and in that case, we would design a bandpass filter. But these are ideal representations of filters, and we can't expect to build a filter that perfectly rejects or keeps very specific frequencies. In our pasta example, sometimes a few noodles snake their way past the strainer, and there is always some water left over clinging to the noodles in the pan, so not a perfect separation of the two. In reality, where a filter transitions from passing to stopping is not a single point, but occurs over a band of frequencies. Likewise, you don't get perfect unaltered frequencies in the pass band region, nor do you always get perfect attenuation in the stop band region. How you design your filter is based on the requirements for the filtering that you are doing, And there are many variations of these types of filters, and they're given names like Butterworth and Chebyshev and Bessel and more. And there's tons of them, and there'll probably be even more in the future. But the point I want you to take away from this section is that almost every filter will have these key features in common, and those features are tied to specific frequencies. So it's important that our final digital filter design maintains these critical frequencies right where we want them. It does us no good to design a low-pass analog filter only to have the transition band move on us when we convert it to a digital filter. So with that being said, let's get back to our original goal of designing a filter for a digital computer. Like our helpful friend suggested, a popular way of approaching this problem is to design an analog filter first, get it just right, and then use the bilinear transform to map it to the Z domain, and hopefully create a digital filter whose critical frequencies have not been moved. The reason we would approach the design with an analog filter rather than directly designing a digital filter is that we have a large amount of continuous analog theory available to us that will give us more tools to use during our design. Let's see how this works in practice by trying it out on a standard notch filter. At this point, you've understood the requirements your filter must meet, and you've toiled over the math and simulations, and you're happy with the following analog filter design, where omega naught is the critical frequency that you want to attenuate, which in our case is 0.1 radians per second, and Q is the quality factor of the filter, or a value that corresponds to the steepness and depth of the notch. In this case, we're choosing Q equals 1. This will generate a magnitude response curve that looks something like this red line. Now, this isn't a video about how to design an analog filter. That would require its own standalone series, so I'm not going to go into detail about how we chose this particular notch filter. For now, just know that this is one possible form of a notch filter that we could have created to meet our requirements, and I'll show you in a bit in MATLAB that this pink transfer function does truly create a magnitude plot that meets our requirements. Okay, so at this point we have a perfectly fine analog filter, but the catch, as you know, is that we want to implement it on a digital computer, and say one running with a sample time of 2 seconds, which means we need to map it to the Z domain using the bilinear transform. We did the calculations by hand in the previous video, so in this one let's just go straight to MATLAB. First things first, let's define our Laplace variable s and then set our sample time to 2 seconds, the critical frequency to 0.1 radians per second, and the quality factor to 1. With our variables defined, we can create our S-domain transfer function using the equation for a standard notch filter. And no surprise, we got the same result that we did by hand. Now let's see the Bode plot to check out the magnitude of this filter across the frequency spectrum. And that's a good looking notch. And if we zoom in a bit, we can see that the notch is located precisely at 0.1 radians per second, just like we wanted. And with step 1 out of the way, let's use the bilinear transform, or the Tustin method, to convert to the Z domain. And we get a discrete transfer function with a sample time of 2 seconds. So far, so good. We can now plot the Bode plots for both the analog and digital filters on top of each other and see how we did. That's pretty good. The red digital filter lies pretty much on top of the blue analog filter. We did some fine work here. And all that's left to do is write some code for this filter and put it on our digital computer. Wait a second. I'm just realizing that I got our original requirement wrong. It looked like omega naught was written as 0.1 radians per second, but really it was supposed to read 0.7 radians per second. Okay, that's no problem. We'll just update the omega naught variable to 0.7, rerun our analog transfer function and discrete time transfer function. Now, this is probably still okay, but let's just check the Bode plot once again to be absolutely sure. And they're different. And if we zoom in, we can see that the analog notch is at 0.7 like we want, but the digital notch is much lower at 0.61 radians per second. What happened? All we did was increase the critical frequency. Well, this shift in frequency comes down to how the Z-plane is warped by the bilinear transform differently than e to the st, which is the true definition of Z. So it should be clear that you can't just blindly apply the bilinear transform to any function with any sample time and get a good match in the Z domain. So what's going on here? To answer this, we must first talk about how Z equals e to the st maps from the S-plane to the Z-plane. I'll just set up a blank S-plane and blank Z-plane, and let's try to convert a few points for a sample time of 2 seconds. We'll start with the origin, s equals 0 plus 0j. This gives us z equals e to the 0 or 1. So the origin in the s-plane maps to the point 1, 0 in the z-plane. Let's try s equals minus 1 plus 0j. And this maps to 0.1353 in the z-plane. This is inside the unit circle and fairly close to the origin. If we head up the imaginary axis to s equals 0 plus j, we see that this maps to negative 0.42 plus 0.91j, which lies on the unit circle in the z-plane. And finally, let's try a point at s equals minus 100, which is practically negative infinity for this system. And it maps to 1.38 times 10 to the minus 87, basically 0. So points near negative real infinity map to the origin in the z-plane. Doing math is fine, it's fine, but I think it helps to be able to visualize the mapping. Here's what it's doing. We start with the Cartesian grid in the s-plane. The e to the real part of s scrunches the left half plane inward to where the entire left half plane exists between the real values 0 and 1. And the right half plane extend out past 1 to infinity. The e to the imaginary part rotates this scrunched grid around the origin, and it just keeps rotating it more and more as omega increases towards infinity. In this way, the j omega line in the s-plane maps to the unit circle in the z-plane. Now, to help with this visualization, let's look at something much more precise than my drawings. I wrote a little program that maps a location in the s-plane on the left to the z-plane on the right using the transformation z equals e to the st. And in this case, t is set to 2 seconds. You'll note that the left half plane is gray, and this maps entirely into the gray unit circle in the z-plane. The right half plane, the white part, is outside of the unit circle. The origin of the s-plane, the red dot, is mapped to the point 1, 0, the black dot. Now, if I move that red dot to about minus 1, 0, you can see the black dot moves inward towards the origin. And if we keep going more negative in the s-plane, it pretty much maps right onto the origin of the z-plane. And if we start heading up the j omega axis, the black dot follows the perimeter of the unit circle. That's because the j omega axis maps to the unit circle in the z-plane. Now here's the interesting part. If we start at a fairly negative j omega value and just start increasing it, you'll notice the black dot rotates around the origin again and again. This is the effect the imaginary part has on the mapping. It just rotates the mapping around the origin, while the real part dictates how far you are from the origin. Now keep that in mind as we contrast this behavior with the bilinear transform. We'll start by drawing out a blank s-plane and z-plane again, and then convert the same 4 points that we did with e to the st, but this time using the bilinear transform. We'll start with the origin in the s-plane, which maps to the point plus 1 in the z-plane, the same as we got before. But this time the point s equals minus 1 maps exactly to the origin in the z-plane. And the point s equals 0 plus j maps to j in the z-plane. Now that's still on the unit circle. The j omega line still maps to the unit circle using the bilinear transform, but the resulting location around the circle has changed. Finally, our point at basically negative infinity maps to about minus 1 in the z-plane. The math is the math, but just like we did before, let's attempt to visualize this mapping and see if we can use that visualization to understand how these two transforms project the s-plane onto the z-plane differently. Again, we start with the Cartesian grid in the s-plane, but instead of scrunching it in from the negative real line, we're going to pinch it in at 3 different locations. We're going to bend the j omega axis down from the top and up from the bottom, so that the tips of the line at positive and negative infinity meet at the point minus 1. Similarly, we're going to pinch the negative real line so that its infinity also meets at minus 1. With this mapping, there are no rotations, just a pinching of the positive and negative imaginary infinities and negative real infinity so that they all meet at minus 1. Again, the pinching is done such that the j omega line wraps around the unit circle. Now let's see what this looks like with a bit more precision. This is the same idea as before, but now we're going to map from the S-plane to the Z-plane with the bilinear transform, still with a sample time of 2 seconds. Just like with e to the st, the bilinear transform maps the entire left half plane to inside of the unit circle. But now look at the way that this grid in the z-plane is shaped compared to the one that we saw with e to the st. The grid gets more dense towards -1 rather than the origin. And if you follow the real or imaginary lines in the s-plane, they all curve towards this -1 point in the z-plane. The origin in the S-plane maps to the point 1, 0 as we expect, and as we move along the negative real line, we can watch the black dot also move along the negative real line closer and closer to -1, but never quite reaching it. And if we move up and down the j omega line, you can see the black dot travel along the unit circle towards -1 as well. So all infinities in this left hemisphere in the S-plane map to -1 in the Z-plane. A bit different than e to the st for sure. Okay, what does this difference in warping have to do with the frequency? Well, let's take the bilinear transform and recognize that s is defined as sigma plus j omega. Sigma is the exponential term which doesn't impact frequency, so we can just look at j omega for frequency information. We can plug j omega into the bilinear transform for s, and we get this equation. Here I wrote omega sub a for analog frequency, because this was the true S-domain location which defined the analog frequency that we wanted. This was our starting point. However, to find out what this new frequency is that we just created, we can convert back to the S-plane using the definition of z, or e to the st. For this s, I'll replace it with omega sub d for the discrete frequency that resulted from the bilinear transform. Now we can just solve for omega d as a function of omega a, and you can tell from this equation that omega d does not equal omega a. We've moved the frequency by using the bilinear transform. We can simplify this equation, but for now, let's try a few points with this unsimplified equation and see how the frequencies move. But before we do that, let's recognize that for a sample time of 2 seconds, or a sample frequency of 1/2 hertz, the Nyquist frequency is 1/4 hertz, or half the sample frequency. This puts the Nyquist frequency at pi/2 radians per second, and we're going to use this shortly. For our first point, let's look at an analog frequency of 0.1 radians per second. This is about 6% of the Nyquist frequency, which is relatively slow. Let's plug this into our equation, and rather than solve it by hand, let's just quickly solve it in MATLAB. First, I'll define the omega a variable, type out the equation for omega d, and we get a discrete frequency of 0.0997 radians per second. You'll notice that this is very close to our starting analog frequency, and it's what we saw when we plotted the discrete and analog notch filters on top of each other when the critical frequency was 0.1 radians per second. Now, let's try an analog frequency of 0.7 radians per second. This is a relatively fast frequency, or about 45% of the Nyquist frequency. Again, we set up our equation to solve for omega d, and then we go back to MATLAB, change our omega a variable, and solve for omega d. The discrete frequency is not 0.7 radians per second, but about 0.61, which, again, if you recall, was the difference we saw between our two notch filters when the critical frequency was 0.7 radians per second. Interesting. So at this point you might be asking, what happens if we design a filter above the Nyquist frequency? Well, let's try it with an analog frequency of 2.5 radians per second. We'll zip through the math real quick, you can double check this on your own, but we find that it's about 1.19 radians per second, which is really different than our goal, and it was mapped to just below the Nyquist frequency. In fact, it doesn't matter how high the analog frequency is, when you map that system using the bilinear transform, it always maps it to just less than the Nyquist frequency. That's the result of the mapping not rotating around the origin, but rather pinching it down to -1. That -1 point is the Nyquist frequency in the Z-plane. Okay, enough of that. The question is, what can we do about this? Well, remember I said that this equation can be simplified. The math is pretty straightforward to do the simplification, but it's a bit much to write out here. Instead, I direct you to follow along with the Wikipedia page, where they do a pretty good job of deriving the simplified equation. And it's this equation here where omega d is this arctan function of omega a. Alright, we are in the home stretch now. I'll rewrite the frequency warping equation here, and if we plot this equation, we find something very telling. As we increase omega a, omega d continues to increase as well, but asymptotically to pi over t, which is the Nyquist frequency. In our case, it's pi over 2 since our sample time is 2 seconds. And what you'll notice is that this equation has nearly a 1-to-1 linear relationship with omega a and omega d at low frequencies compared to the Nyquist frequency. And as we increase omega a, omega d differs from it more and more, just like we saw with our design. So, I ask the question again, what can we do about this? Well, we can pre-warp omega a. Essentially, this means that we are artificially moving our design frequency before mapping it with the bilinear transform, so that after the mapping, the critical frequency is in the correct spot. To do this, we apply the tangent equation to omega a first. Luckily, there is a way to do this pre-warping at the exact same time that we do the bilinear transform with a modified version of the transform. Instead of having a multiplier of 2 over t, we multiply z minus 1 over z plus 1 with omega naught divided by the tangent of omega naught times t over 2. And, we could do this mapping by hand, but again, we could just do it in MATLAB as well. Once again, we'll set up our variables and define our S-domain notch filter at 0.7 radians per second. Then we can convert it to the z-domain with the bilinear transform, but this time we'll apply a pre-warping at 0.7 radians per second during the conversion. Remember, when we did this without the pre-warping, our discrete notch filter came back at 0.61 radians per second. So let's see how this one does. And it's perfect. Look at this. If we zoom in, we can see that with the pre-warping, we were able to create a notch filter with the desired critical frequency. Okay, that's pretty much what I wanted to cover in this video. Just that we can use the bilinear transform to convert analog filters into discrete filters, but we have to understand how frequencies are warped during this process and account for them during the conversion. So thanks for watching and following along with this extremely long video. But before I leave you, I promised that we would end with a pretty sweet animation. Well, I think it's sweet anyway. Once again, I present the Z-plane and its unit circle. I'm going to use this to show you exactly what is happening when we apply a pre-warp at a specific frequency. I'm plotting 4 poles here. The 2 on the far right are the 2 notch filter poles for the critical frequency of 0.1 radians per second. And the 2 on the left are the notch filter poles for the critical frequency of 0.7 radians per second. These are the true locations of the poles when converted using z equals e to the st. The grid pattern you might recognize as the mapping that occurs when using e to the st. Now, I'll add on top of this the exact same 4 poles, but this time mapped using the bilinear transform. Notice the 2 on the right overlay nicely. This agrees with what we saw before, which was that relatively low frequencies compared to the Nyquist frequency don't get shifted by very much. However, look at the 2 poles for the 0.7 radians per second critical frequency. Not close. And also exactly what we saw before. Now watch as I apply a pre-warp at a larger and larger critical frequency. The whole red grid starts to move and stretch, and moving the poles along with it. And if I stop exactly at 0.7 radians per second, you can see that all 4 poles for the 0.7 radian per second notch filter line up with each other. Now in doing so, the 4 0.1 radian per second poles no longer line up, but that's the penalty we have to pay with the bilinear transform. We have to choose the frequencies that matter most to us. But all in all, the bilinear transform is pretty awesome. Okay, that is the end of this video, finally. A huge thank you to my Patreon supporters for making this video possible. If you would like to support me in my efforts on YouTube, you can from the Patreon link in the description below. For any amount of support, you can download a digital copy of my book in progress on control theory. Now, I'm still actively writing the book, so it's not complete. But if you would like a copy of what I have so far but are unable to support through Patreon for any reason, just email me at controlsystemlectures@gmail.com and I will send you a copy for free. That way we can spread the knowledge and help everyone on their quest to becoming better control system engineers. Thanks, everyone.